Last week, I suggested a diet called the glass noodle diet, which is a diet that is both high in starch and very low in protein. And specifically, it's low in the branched chain amino acids, isoleucine, valine, and leucine. The specs of this diet is a starch-based diet where the quote-unquote protein foods are limited to the equivalent of 6 ounces of lean meat, which is about 35 grams of protein that could come from meat or eggs or dairy products. The goal is to have at least 1 ounce of protein from gelatin, so that's 28 grams, which could come from something like bone broth or chicken stock or powdered gelatin. Fruit and non-starchy vegetables are fine on the diet, but one of the keys of the diet is to not blow your protein budget on protein from grains. So that means in this diet, we're not consuming rice, corn, wheat. We're consuming things like cassava and cassava flour and glass noodles, which are made from purified starch. And these things are all extraordinarily low in protein and low in branched chain amino acids. Launching of this diet concept caused some consternation on the internets. So let's start here. This is an excerpt from a paper about branched chain amino acids, but I just like the short description of the problem. It says a common manifestation in obese individuals with insulin resistance is the inability to shift from fatty acid oxidation in the fasted state to glucose oxidation in the fed state, also called metabolic inflexibility. They go on to talk about the Randall cycle. You can see Randall et al. There, and they say byproducts of fatty acid oxidation such as acetyl-CoA, NADH, and ATP act as potent allosteric inhibitors of glycolysis, and that PDH is the pyruvate dehydrogenase complex. And if you don't have an active pyruvate dehydrogenase, you cannot burn glucose effectively in your mitochondria. And it says several studies in animals reported that accumulation of branched chain amino acids and its derived metabolites can also directly inhibit pyruvate dehydrogenase activity. So these branched chain amino acids are directly inhibiting the thing that allows you to burn glucose, among many other issues that they're causing. So in my proposal of the glass noodle diet, these are the levers that we're pulling to hopefully regain our insulin resistance and our metabolic wellness. The fact that the diet is high in carbohydrate will decrease that NADH and it'll increase NAD+. And NADH is one of those allosteric inhibitors in the Randall cycle that doesn't allow you to burn carbohydrates effectively, and that gives you glucose resistance or insulin resistance. Another lever that we can pull is using oxidants such as alpha lipoic acid. I prefer RALA, it says on the bottle, and that is another thing that decreases NADH and it increases NAD+. Another lever that we can pull is stearic acid signaling, and I'm going to talk about how stearic acid levels have declined over time. I sell a product at fireinaBottle.net/shop called stearoyl ethanolamide, SEA, which is the way that stearic acid is used by the body as a signaling molecule. I apologize, it's been out of stock for a while, but we do have it back in-house. Everything should start shipping next week. So if you've ordered, you should have the product in hand next week. And if you haven't ordered yet, this is your chance to go over to fireinaBottle.net/shop and get some. This diet, by increasing glycine, and glycine is one of the main components of gelatin, will help decrease acetyl-CoA in your skeletal muscle. And I talked about that in last week's video titled The Optimal Omnivore. You can see how glycine removes acetyl-CoA and again gets you out of that stuck position in the Randall cycle where you can only burn fat and you can't burn glucose. And then finally, by restricting protein and by restricting branched chain amino acids, we can reduce mTOR signaling, and we'll talk about what mTOR means briefly, and you can increase FGF21 signaling, and we'll spend a little bit more time talking about what FGF21 is. Let's start with stearic acid signaling, because this really is the kind of long-term goal of this diet, is to restore our stearic acid signaling by resaturating our body fat. I'll show a couple slides showing how our body fat has changed. This is a study using SEA in rats. And so they fed these rats a high-fat diet that was designed to make them insulin resistant. And then some of the rats were given stearoyl ethanolamide, which is NSE. In this study, what I sell on my site is SEA, but it's the same thing. So this is tissue necrosis factor alpha, which is involved in inflammation. And it's known in mammals to increase lipolysis, which is to increase the release of free fatty acids from your adipose tissue, from your fat tissue, to feed the rest of the body. And if you have high TNF alpha, that means you're going to be stuck on one side of the Randle cycle. You're going to be stuck on burning fats, and you won't be able to burn carbohydrates because your fat cells are going to be releasing all these fatty acids. These rats were made insulin resistant and then given steroidal ethanolamide, and you can see the TNF alpha levels return to normal. And you can see this is their insulin resistance score. The insulin resistant rats were up to 1.34. And with the steroidal ethanolamide, they went back down to 0.75. And this is just a little short description of that. You can see TNF alpha secretion is positively correlated with obesity and may contribute to insulin resistance by increasing serum non-esterified fatty acids, and that also is known as free fatty acids. Another factor that I haven't talked about is this thing called mTOR, and so this gets directly at the branched chain amino acid restriction. You can see one of the primary stimuli to which mTORC1, which is one of the forms of mTOR, is responsive is the availability of amino acids, particularly the branched chain amino acids leucine, isoleucine, and valine. In obesity, you tend to have high levels of circulating branched chain amino acids. In this diet, we're going to remove those branched chain amino acids from our diet or restrict those branched chain amino acids to get those levels down. One of the things they're doing is they're activating this mTORC1, and you can see mTORC1 is involved in adipogenesis and lipogenesis. You can see it actually blocks the thing that blocks SREBP1, so that's the same as activating SREBP1. And SREBP1 is the master transcription factor of lipogenesis. A transcription factor is a thing that just turns on other genes. So when this is active, you're going to make more fat through the process of what's called de novo lipogenesis. Anyway, and so I'm not going to linger anymore on those topics, but these are a lot of the questions that came up in the comments on here and also over in the Reddit thread r/saturated fat. That's a great discussion of these topics. You should go over there and get into that discussion. And the questions people had were about protein sufficiency. When you suggest that people should restrict protein, a lot of them lose their minds. Are you sure this is enough protein? Is this safe? Are you insane? You're going to lose muscle mass. Another question is this a forever diet? A lot of what I talk about is returning to a world where we can eat a traditional French diet or a traditional American diet, which has a lot of saturated fat with starch in it. So we'll get to that. Another question is about antioxidants. In the last video, I suggested that glycine and cysteine together would restore glutathione, which is the body's master antioxidant. And in general, I'm not a fan of antioxidants, but I'll explain why we want glutathione, but we don't want exogenous antioxidants, which is something that we're adding that's not part of our body's normal system. And then people had questions about oxalates because I suggested cassava flour as a source of starch that's very low in branched chain amino acids. And some people have real concerns, fair concerns with consuming too many oxalates. So let's start with the antioxidant question. This is glutathione. This is our body's master antioxidant. This is superoxide. That's the main free radical that is produced during our metabolism, and that can actually be produced in the cytoplasm by an enzyme called NOx, which is NADPH oxidase. And so what NOx does is it just takes NADPH, and NADPH is an electron carrier, and it takes those electrons from NADPH and it just gives them to oxygen, and it just spews out this superoxide, this free radical. And after that gets converted by superoxide dismutase to hydrogen peroxide, glutathione comes along and it converts that hydrogen peroxide back to water harmlessly. So this GSSG is now oxidized glutathione. And the magic of this system is that every time one thing gets reduced, if you have too many reduced things, you're in reductive stress. If you have too many oxidized things, you're in oxidative stress, and things can cycle back and forth. And so this GSSG is the oxidized glutathione. And so there's another enzyme that can take this and reduce the glutathione. And when that happens, the NADPH is the thing that gets oxidized. The reason it's called redox is every time something gets reduced, something else gets oxidized. To make glutathione, you need cysteine and you need glycine. You also need glutamate, but that's not terribly hard to get. And so in the last video, I talked about supplementing. I talked about glycine coming in this diet in the form of gelatin, and perhaps you could consider supplementing with something called N-acetylcysteine. These things come together to make glutathione. That increases the amount of antioxidants that you have. But the great thing about that is our body's internal antioxidant systems actually oxidize the NADPH pool. So having an effective glutathione system, every time that something like NOx is making superoxide, you're going to use this superoxide as a tool to oxidize the NADPH pool. And why is that good? Why do we want to oxidize the NADPH pool? Well, NADPH is actually used in the process of de novo lipogenesis. This is how DNL works. NADPH is the starting point. So if you have a very reduced NADPH pool, you're going to do a lot more de novo lipogenesis. You're going to make a lot more fat. If you can oxidize this NADPH back to NADP plus, you will not be able to do as much de novo lipogenesis. Furthermore, if you have too little reduced glutathione that can eliminate this hydrogen peroxide, you can wind up with legitimate oxidative stress. So you do want to have a healthy pool of glutathione, both to prevent yourself from oxidative stress, but also to keep your NADPH pool oxidized, and so you're not doing too much DNL. You can see how those antioxidants work in a couple. These are a couple mouse models, and so this is a high dose. This is a mouse on the kind of black line here is a mouse on a high fat diet. And they certainly get obese, but if you give them a high dose of this antioxidant in this experiment, they actually even get fatter. If you give them an antioxidant, you're mopping up all of that superoxide. If you don't have superoxide, you can't oxidize the NADPH pool. You do more de novo lipogenesis. This is another model. So these mice don't have NOx. So they don't have the enzyme that creates the superoxide in the first place. They also become fatter. And this is actually on a low-fat chow diet. Mice on a diet that would normally remain thin, you can make them fat just by removing the enzyme NADPH oxidase, which helps to keep that NADPH pool oxidized. One of my favorite supplements, I talk about it all the time, R-lipoic acid, is an oxidant. And so before we were talking about de novo lipogenesis, which happens in the cytoplasm, R-lipoic acid acts in your mitochondria. And so these people were taking a food that was enhanced with ALA over a series of months. Remember, in that Randle cycle, one of the things that's inhibiting your ability to burn glucose is you have too much NADH in your mitochondria. RALA targets the mitochondria and it converts NADH to NAD+. So it gets rid of that NADH, allowing you to burn glucose. So this is their fasting glucose. Went from 120 at baseline to 102 after 3 months. So that's a pretty significant reduction. And this is their postprandial glucose. Went from 164 to 141, and I think that's 2 hours after they ate. LDL production dropped with the ALA. CRP is an inflammatory marker, dropped significantly. MDA is another, that's a marker of actual lipid peroxide due to oxidative stress. That decreased significantly, all because we're oxidizing that NADH pool. Did I mean to intend for this to be a diet that we consume forever? I did talk about long-term, you need some protein in your diet. And what I meant by long-term was really if you use this diet for 3 months or 6 months or a year or 18 months to get back your metabolic health. And at that point, what I foresee doing is starting to add back higher protein sources, starting to add back more saturated fat, things like butter that they use in France, because butter is something like 70% saturated fat. So that's the best fat to add back once you feel like you've regained some of your metabolic health and you can start to experiment. But what I want to point out is the goal of this diet really is resaturation of your body fat. So this study is just showing the literal effects of changing the NADH to NAD plus ratio. So they use this thing which inhibits this enzyme that regenerates NAD plus. And so you get stuck with a high NADH to NAD plus level. And that increases all of these enzymes involved in de novo lipogenesis. But these things all kind of act in the short term. SCD1, what it does is it converts stearic acid to oleic acid, and that oleic acid builds up in obesity, and this has real long-term effects. So this is like the thing that can weigh you down forever as you try to get back. And so what you really want, and what you can see is that SCD1, when NADH is high, SCD1 is increased. when NADH is low, and what they did here was they just supplemented with NAD plus, right? And so now these cells had all the NAD plus that they wanted, and SCD1 levels dropped by about half compared to control and about threefold compared to the ones that had high ratio of NADH to NAD+. This study was published in the early 1960s, and they looked at people around the world. Nigerians were eating a lot of starch. Colombians were eating a lot of starch. And you can see their fat was about 40% saturated. And what they point out here, even in 1960, they knew that this ratio of stearic acid to oleic acid was important. And when this number is low, that means you have more stearic acid, and that means you have low SCD1 activity. By 1998 in America, our saturated fat levels had dropped all the way down to 24. So they went from 40 down to 24, and that ratio of oleic to stearic acid was all the way up to 16. So compared to a tribe in Nigeria eating starch, Americans in 1998 had 3 times the level of SCD1 activity. That shows up as a lack of stearic acid, and you're going to have low stearic acid signaling. So this is not a forever diet. The goal is to lose weight. The goal is to become insulin sensitive. The goal is to resaturate. So, but what we needed, right? We need a tool that can do these things in the short term without restricting calories. And so what I'm saying here is we need ad lib calories. We need to eat till we're full. And part of the reason for this is just so that people stay compliant. But the bigger reason is there are real problems that are caused with caloric restriction. I talked about in my video, the dark side of caloric restriction. I'm going to show you another dark side of caloric restriction in the next couple of slides. But yes, the idea of this diet is you use it for 3 months to 2 years, something like that. And you escape torpor, and that is important, right? Torpid animals who are hibernating, who lower their metabolic rate, they also have elevated SCD1 levels, and they also have a lot of monounsaturated fat compared to the amount of stearic acid that they have. Can I justify this amount of protein restriction? There was a lot of people are very concerned about this concept. They think they'll lose muscle mass. And so I just want to point out a real world example. So the country with the highest per capita consumption of cassava is Ghana. And so Ghana is right here with the G. And it's part of this cluster of countries in West Africa who have extraordinarily low levels of diabetes. This is Angola. Angola is also consumes a lot of cassava. So I did a little analysis of the Ghanaian diet. This data is all pulled from FAO Stat. So in this day and age, Ghana has no lack of calories. There's plenty of calories to go around. And this is all in calories per capita per day. What happens in Ghana is they don't eat a ton of cereals, grains, compared to a lot of poorer countries, because they're eating a lot of starchy roots instead. So this is 1,200 calories from starchy roots. A lot of that is from cassava and also yams, and also, sorry, I stuck it down here, plantains is another source of starchy roots that are high in starch, very low in branched chain amino acids. I just did a little comparison down here. So 100 grams of potatoes have about 80 calories and provides 0.27 grams of branched chain amino acids, whereas the same weight of cassava has twice the calories and about 1/3 of the branched chain amino acids. And so cassava really is a very low BCAA food. And Ghana, the average protein consumption is around 8% of calories, and they only have 2.6% rate of diabetes. You see that a whole country is surviving indefinitely on the amount of protein that I've suggested, and they have low rates of diabetes. And so I think that in terms of a short-term diet, this is a pretty good check that what I'm suggesting is not outside of the realm of the human experience. The other thing, so when you have elevated BCAAs, you activate mTOR. mTOR causes you to produce more fat, and it causes you to produce more protein. It's very anabolic. It causes you to make things, right? The reason I bring that up is if you look at, so this is old data. I think this is from 1975, but if they look at normal lean humans, so this one over here is men, but the same thing is true in women. These men had about 58 kilograms of fat-free mass. So that means muscle, bone, blood, brains. Well, maybe not brains. And these are muscular men. It's a little bit ill-defined, but but the muscular men had 69 kilograms of fat-free mass. And the thing is, the obese men had 73 kilograms of fat-free mass. So the obese men actually have more muscle than the quote-unquote muscular men. Notice when I thought about this is if you're actively losing weight, if I'm going to get down from my current weight, that extra fat-free mass in the obese is mostly skeletal muscle, right? If you figure that out, 15 kilograms of muscle tissue is about 20% actual protein, actual amino acids. So that suggests I would have 3 kilograms of amino acids that I'm going to break down as I lose that weight, right? And so just that extra reservoir of amino acids that I have on my body that I hope to break down, that's going to supply me with 50 days of protein. All right, so here's how these branched chain amino acids are broken down. There's this enzyme called branched chain keto acid dehydrogenase, and this is a very similar protein to pyruvate dehydrogenase that has all the same subunits. It uses alpha lipoic acid as a cofactor. It works in essentially the same way as pyruvate dehydrogenase, but this functions on the protein side, whereas pyruvate dehydrogenase functions on the carbohydrate side. And so all these amino acids are ultimately broken down and can be burned in the TCA cycle or can be made into ketones. But then if the question is, why do I have elevated branched chain amino acids? Well, we can think again about the model of torpor as a model for human obesity. So these are squirrels that are in torpor. You can see I have circled here late torpor. And what we're looking at is these 3 breakdown products of the branched chain amino acid pathway. And it says the pattern of these 3 things was suppressed relative to summer active squirrels. So this is how much they have of these things in the summer. This is how much they have in late torpor. And they are suggesting a general conservation of branched chain amino acids during the hibernation season, which is to say that the reason that you have elevated BCAAs is that you're in torpor. If you look at humans who are obese compared to lean humans, we have low expression of branched chain keto acid dehydrogenase in our adipose tissues. This is another experiment in mice showing again that these branched chain amino acids are actually causal in obesity and not just associated. So these mice are all put on a Western diet, and they actually manipulated individual branched chain amino acids. So the mice in black are on a Western diet. The mice in gray are on a Western diet, but they don't have as much leucine. And restricting leucine out of the branched chain amino acids didn't make any difference. But if they restricted isoleucine, the mice lost weight dramatically. You can see this only took 4 weeks until mice who didn't get isoleucine in their diet were leaner than the control mice. And you can see those mice actually ate the most food. And so you can say, okay, well, something about restricting branched chain amino acids or specifically isoleucine caused their metabolic rate to increase. Otherwise, they wouldn't be able to eat all of these extra calories, right? That's a lot of extra calories, and their weight is plunging on this diet. Furthermore, you can see the mice that didn't get leucine are very glucose tolerant. So this is a glucose tolerance test. They give them a lot of glucose, and they have this very low spike of blood glucose. And this is a glucose infusion rate. So these are mice on the Western diet, and these are mice on a Western diet that don't have isoleucine. And you can see the amount of glucose that they can oxidize or absorb and make into glycogen is about 2.5 times of mice given a normal Western diet that is full of the branched chain amino acids. And so these results with the BCAA restriction are pretty dramatic. Here they show the actual thermal output. This is metabolic rate essentially of mice with the isoleucine restriction. You can see it's massively increased. And they say that the benefits of isoleucine restriction are mediated in part by FGF21. So this is probably not the whole story, but it's an important part of the story. They look at the mice. These are mice again on the isoleucine restriction. The growth factor FGF21 is doubled in the liver, doubled in this is white adipose tissue, that's fat tissue, and it's tripled in the muscle of these mice. If you take FGF21 and inject it into mice that are on a high-fat diet, they will lose weight. So all these mice are on a high-fat diet. The ones given the highest dose of FGF21 lose the most weight. You can see again, this is another glucose infusion test. How much glucose can these mice take? The mice on a normal high-fat diet are very glucose resistant. If you give them a high-dose FGF21, they can use glucose again. And SREBP1, we talked about this before, the master lipogenic transcription factor, the higher the FGF21 goes, the lower the amount of mature SREBP1. And so FGF21 lowers lipogenic enzyme expression. And look at this. Look what happens to SCD1 in mice injected with high dose FGF21. It plummets by 75%. And so again, when we think about long-term changes that we want to see, we want to lower levels of SCD1 and increase our stearic acid signaling. This is my favorite part of this study. They looked at the metabolic rate, and you can see this is over 7 days. So in the beginning, when they start injecting the FGF21, the metabolic rate isn't that much different when you look at the blue dots versus the red dots. It's a little higher, but they're almost working in parallel through the first day or two. By the end, the high dose FGF21 metabolic rate is just absolutely ramped. This peak here is about 155 as opposed to the mice that don't get the FGF21 is about a 128. That's about a 20% boost in metabolic rate just from this FGF21. This is a different experiment. So they gave them 4 different diets and they looked at FGF21 levels. And this is a low protein diet, right? So they're restricting protein and they're getting a normal amount of calories. And you see this huge spike in FGF21. These mice also have restricted protein. They're also LP is low protein, but they're on caloric restriction. And if you restrict calories, you do not get that bump in FGF21 that comes from the protein restriction. This is a test in humans. So humans went on a protein restricted diet for 28 days, had their FGF21 levels checked. 8 out of 8 humans during protein restriction had FGF21 levels increase, obviously some more than others. If you follow this person, they had a 7-fold increase in FGF21 levels from restricting protein. This is another trial in humans where they restrict protein. Again, it's pretty short term. It only lasted 43 days on average. You can see this is the composition of the diet. Protein goes from 17.4% that they were eating down to about 8.3% on the diet, which is about how much protein that they consume in Ghana. That's about the levels that I'm kind of suggesting on this diet. And carbohydrates increase, and that's partially because they're replacing the protein with carbohydrate. This diet is also a little bit lower in fat, and so some of the fat is also replaced with carbohydrate, and they get the carbohydrate up pretty high, 59%. So they made all the food for these people. They gave them the meal so that they could control the protein and the carbohydrate and the fat percentage. You can see that the energy intake was not restricted. That was 2,800 calories a day. Over the course of 40 days, the people on the protein restricted group lost about 5.8 pounds on average, and 3 pounds of that was actual fat mass. That is a pretty good result. And while they were on this diet, FGF21 levels doubled. And you can see the study did what was supposed to happen. Leucine levels dropped, isoleucine levels dropped, and valine levels all dropped. These are factors that affect circulating FGF21 levels, and so a high carbohydrate diet does really increase it. A low protein diet, of course, increases it. Alcohol actually super increases it. Eating fat also increases it. So it's possible that on a low protein ketogenic diet where you're consuming a lot of fat, but you're consuming very little protein, that you could also increase FGF21. And so the FGF21 story is a little bit nuanced. People who are obese actually have higher levels of FGF21. And it seems like this is mostly due to a lack of the FGF21 receptor in things like adipose tissue, which is called klotho. You may have heard of beta klotho or alpha klotho. They're very popular in longevity research. The receptor for FGF21 in a lot of tissues is this protein called klotho. And this is in humans with type 2 diabetes. And you can see the klotho drops by about 75%. And so that is probably one of the reasons why in obese in diabetic humans, you see high levels of FGF21, and yet they're having these metabolic issues. This is back in mice, and this is another question about the ketogenic diet. So the ketogenic diet also decreases this beta-klotho mRNA dramatically, and this phosphorylated ERK is a sign that FGF21 signaling is working. And in the ketogenic mice, you have this drop in effective FGF21 signaling. So that was more of the rationale behind the low protein diet, the presumed safety of it, why we're doing it, what are the underlying metabolic effects we're hoping to get from it. I also want to address people's concerns about oxalates found in cassava flour, which is one of the products that I suggested using on this diet. Oxalates can be a real problem for people. They can form kidney stones. Some people seem to have worse outcomes consuming a diet that's high in oxalates compared to others. This company, GF Joules, makes a whole bunch of products that are using purified starches. So the purified starches don't contain oxalates. So if you're consuming the glass noodles that I talked about in the last video, so sweet potatoes are also relatively high in oxalates, but the sweet potato starch, the purified starch, don't have the oxalates. So you can eat the sweet potato starch noodles. You won't get a ton of oxalates from it. Anything made by this GF Joules company are using more of the refined starches, it seems like. So all of their products seem like pretty safe options for doing pancake mixes, etc. Here's another product that I stumbled across. They had it at Wegmans this week. This is a very interesting product. It's a little bit mind-blowing. So they make this gluten-free flour, and you can see there's no protein in it, but the main ingredient is gluten-free wheat starch. So they actually took wheat, they isolated the starch out of it, and they removed enough of the gluten that they've met the FDA requirements for gluten-free foods. They've met the European regulators' requirements for gluten-free foods. And so these guys have a process of literally just taking the wheat, getting the starch out of it, and removing the gluten. And I've tried this flour. It's actually very good. I've made pancakes with it. I made some tortillas with it. This product comes with a recipe for pizza. I might try it this week. Of course, if you do pizza, you want to limit the amount of fat that you put in the dough. I would recommend a tablespoon of butter instead of this 35 grams of oil. That'll only put you at 5% of calories from fat or something like that. And then just, take it easy with the amount of cheese that you put on the top, of course. Use a fat-free tomato sauce, etc. Kind of want to walk people through what a day's eating for me looks like on this diet. I've been doing this about 4 days now, and it's going pretty well. I like the food. I'll have some creative things. I've got some great recipes I'm going to release in the next week or two. I'm just waiting to get some ingredients so I can show you guys what to do. But this is a very simple one, and this is what I've been eating for breakfast most days. It's just a half cup each of the cassava flour and that Fiorglut, the gluten-free Italian flour. It's a little bit of baking powder, a pinch of salt. I put 1 egg in there. The pancakes come out very dense without any egg, so I'm choosing to use a little bit of my protein allotment for the day on these pancakes. About a cup of water and a tablespoon of gelatin, and the gelatin is just there to give me the glycine. And then I put maple syrup on these, and see the macros are about 86% carbohydrate, about 8% protein, and about half of that protein is from the gelatin, and about 6% of fat, which all comes from the egg yolk. I find this to be a very satisfying breakfast. I eat these pancakes around 8 or 9 a.m., and I usually don't have another meal until around 2 p.m. Yesterday, lunch was very simple. I don't like to have a big meal in the middle of the day, so I just made a big salad. I sliced up an apple. I had some pickled beets and shredded carrots on there, and I used this fat-free balsamic vinaigrette dressing they have at the local supermarket. It was a fine meal. It filled up my belly, and I was fine to float through the afternoon until my second large starchy meal at 6 p.m. I have been doing a lot of the glass noodles on the first 3 days of the diet. Yesterday it was rainy and cool, and I was feeling like comfort food, so I actually made chicken and dumpling soup. Dumplings are essentially the dumpling recipe is actually very similar to the pancake recipe. You just essentially make pancake dough, and you just take 2 spoons and you scoop out a little bit of that dough, and you use the other spoon to drop the dumplings into boiling water. The dumplings cook in like at 3 minutes. And then you just add chicken broth, and I used a little bit of canned chicken because it has the same texture as the chicken in Campbell's soup, to be honest. And I have a weird fascination with meat that comes in cans. And this is pretty much the whole recipe. I mean, you can see I added some onions and garlic and a little bit of shredded cabbage and carrots to that. And so the protein in this one checks in a little bit higher, 17%, because I used a chicken bone broth in this. So it's a pretty gelatinous soup, but so we're still going to fall on a daily basis right about where the specs. After dinner, I drank my bottle of wine, which I allow myself. And so that comes to, on a whole day, that's about 2,500 calories. It's about 68% of calories from carbs, and it's only 8% from protein and 5% from fat. So that is well within the macros. I did not go to bed hungry. I didn't go to bed remotely hungry. In fact, the large starchy meals, I feel like, keep me full for hours and hours. I'm getting better at making Asian noodle dishes, just watching YouTube videos and looking for different seasoning ideas. The high carb, low protein diet should restore your insulin signaling. It should restore your FGF21 signaling, and it should reduce your mTOR signaling. And if you do all of those things, this should put you in a position to be able to lose weight and to start to resaturate. And that resaturation is really the big win. Those are sort of short-term goals. That's how the thing works. But in the long term, this diet should allow you to decrease SCD1 levels. Over time, you should be able to rebuild your levels of stearic acid. You should be able to get that stearic acid signaling back. Once you're at target weight, once you're metabolically healthy, you should be able to start incorporating more high protein foods. At that point, if you're out of torpor, your branched chain keto acid dehydrogenase makes superoxide. It makes reactive oxygen species just like pyruvate dehydrogenase does. So once you're out of torpor, once your BCDH is working, once your BCKDH is working effectively, protein actually becomes thermogenic. Branched chain amino acids become very thermogenic. The branched chain keto acid dehydrogenase is one of the most thermogenic enzymes in your whole metabolism. It's just you have to get out of the weeds first and get that thing working first and get out of torpor, and then you can use protein to actually increase your metabolic rate, instead of having those extra branched chain amino acids holding you back. At that point, you should also be able to experiment with, like I said, adding more butter into your recipes and essentially getting back to a classic French style meal, which is heavily carbohydrate based, a lot of things like baguettes, but you're also using them with butter. You're also eating meat and eggs and cheese, etc., as long as you keep it saturated.